Hello. So today we're moving on to a new section in Chapter 8 on bonding theories. We are going to talk today about how bonding actually occurs with orbitals and the concept of orbital overlap. Then we will talk about another concept called hybridization. Basically, the idea of S and P orbitals is a little too simple to explain what we observe around bonds. And finally, we will end this section by looking at the shapes of molecules. And so by the end of this section, you will have one of the major skills of this chapter, which is to be able to draw a Lewis dot structure, and then from that Lewis dot structure, predict the shape of the molecule. Because the other properties of the molecule, like polarity or intermolecular forces, are dependent on the shape. So we talked about this very simply in previous chapters, that how covalent bonding occurs is that the orbitals must overlap so that the electron can actually be shared by those two atoms. So how does that happen? So there's two specific types of orbital overlap that can occur. The first type is called a sigma bond. A sigma bond is an orbital overlap where the overlap occurs on the internuclear axis. It is the strongest type of orbital overlap, and it allows for rotation of the bond. So what do I mean by that sentence? The internuclear axis can be defined as the axis, the line, between the two nuclei. So if I have, these are just two atoms here, the internuclear axis is the line that connects the two nuclei. And you can see when these come together, the orbital overlap is between them. That's a sigma bond. Here are two p orbitals. Remember, p orbitals look like peanuts or dumbbells, and you can see that this part of the p orbital is going to overlap with that part of the other p orbital, and it's on the internuclear axis. Therefore, we would call that a sigma bond. If we have sigma bonds, that means there's probably going to be another type of bonding, right? This picture here shows us the two different bonds. This is the molecule ethine. And there's a triple bond in between those two carbon atoms. We are going to talk about that in a moment, but I want to just focus on the single bonds. The single bond between carbon and hydrogen, if I draw a line between the nuclei of those, do you see how this bond is on the internuclear axis? I can do the same thing over here, right? So this here is a sigma bond. You can also see that there is a bond right here in the middle between those two carbon that's on the internuclear axis. So that triple bond in carbon also contains one sigma bond, but the other bonds you can see here are labeled as pi bonds. What is a pi bond? So a pi bond is where the orbital overlap is above and below the internuclear axis. It stops rotation. So rotation can now not occur when you have a pi bond. So what you see here are two p orbitals, and pi bonds occur with p orbitals. That's easy to remember. If I look at this p orbital here and this p orbital here, look at where the orbital overlap occurs. It occurs above and below the internuclear axis. Because this orbital overlap occurs above and below the internuclear axis, you can kind of imagine if we twisted this bond, then those two lobes of the p orbitals would no longer line up. So there would be no rotation around that. I'm going to go back to our picture here of ethine. So these p orbitals are spread pretty far apart, and it's just for the simplicity of the picture. But if you look up here, here's one p orbital, and here's the other p orbital, and the orbital overlap would occur on the top and the bottom. There's another p orbital in here. It's harder to see because it's the one that goes into the paper, and this guy would be coming out of the plane of the paper, right? So this guy goes into it and he comes out, but the orbital overlap would still occur behind and in front of that. The green bond and the blue bond is what makes up the other two bonds of the triple bond between carbon and carbon in ethine. And so what do you need to know about sigma and pi bonds? Well, you need to be able to define them, what makes the difference between them. And then you also need to be able to count how many bonds of each type are in a molecule. And so this is really the most important piece right here, is that a single bond is one sigma bond. A double bond is one sigma and one pi. And a triple bond is one sigma and two pi. So in any molecule that you look at now, you should be able to identify how many sigma and how many pi bonds there are. Resonance would count as a pi bond, because it is more than just a single bond. The way that those electrons sort of are dispersed throughout the molecule would be through these pi bonds.